Hi everyone, welcome back to Math 256. This is Scott. Let's get started. What we're now going to do is pick up where we left off and build on what we were learning in section 5.5, but now expand it into slightly new terrain. So this is section 6.1, Stability and the Phase Plane. So the setup is that we are going to have an autonomous system in two variables, but not necessarily linear. Not necessarily linear. So then the notation we'll use will be something like x prime and y prime. Sometimes we'll use x1, x2, but often we'll just use x's and y's here. Be some function of just x and y. It's autonomous, so that means it's not a function of t. But it's not necessarily linear, so this function can be of basically any kind. And then g of x is also a function of x and y. So not functions of t. That's the important thing. That's what makes them autonomous. So they are not functions of t, just of x and y. But these are derivatives with respect to t. So then what we'll be looking for are critical points. And these are points where f and g are both 0. And they have to both be 0 simultaneously. So for example, if we had a system like x prime is equal to 12x minus 3x squared minus xy, and y prime is equal to 12y minus 3y squared minus xy, so basically all the x's become y's, all the y's become x's, then we would be looking for the pairs of values x and y that simultaneously make this 0 and this 0. And the way you go about this is the usual way. You go about finding zeros, which is you factor, and then we'll just have to consider some possibilities. So 12 minus 3x minus y is what I would get if I factor out the common factor of x that is shared by all of those terms, and down here, same but with y. With y for x and x for y. Okay, now we need this to equal 0 and we need this to equal 0. So let's think about first off what the first one equaling 0 will force for us. Minus 3x minus y equals 0. So this gives us a branch of two possibilities here. We either have x equals 0 or we have 12 minus 3x minus y equals 0. Well, under this case, we would also need y prime to equal 0. And what that's going to mean is that we're going to have y times 12 minus 3y minus 0 equals 0. In other words, y times 12 minus 3y equals 0, which gives us the two possibilities that basically indicate that y could equal 0, or this one would be y could equal 4. So now these were both under the umbrella of x equaling 0, so it's going to be 0, 0, and 0, 4 are going to be the two possibilities that came from x equaling 0. But it could be the other factor in the x prime equation that equals 0, so maybe it's this that equals 0. And let's just figure out what that would imply. So one thing that we can notice is we could rewrite this as 12 equals 3x plus y. And then if we were to take the equation y times 12 minus 3y minus x equals 0, we could basically, we could just essentially plug this in for 12 and see where that takes us. So y times 3x plus y minus 3y minus x equals 0. And, you know, there are more systematic ways of doing this, but you can also just kind of put things together until you figure out where you stand. And simplify this a little bit, 2x minus 2y equals 0. So this leads us to either y equals 0, in which case if we look over here, that's going to mean 12 equals 3x plus 0, which means x is going to equal 4. Or y equals x, in which case 12 is going to equal 3x plus another x. So in other words, 12 equals 4x, so x equals 3. Now, in this first case, we already knew what y would equal, and in the second case, we would have y equals 3. So this gives us 2 more points, 4, 0, and then 3, 3. So those are our critical points. So we've got 0, 0, 0, 4, 4, 0, and 3, 3. Now, what happens at these critical points is actually going to be very similar to what happens at the origin in section 5.5. And then note the behavior of solutions. Near critical points is the same as the behavior of linear systems near the origin. Near the origin. So in other words, so C section 5.3. So the gallery of behaviors that we saw then apply now as well. So in other words, we can classify these behaviors as, and then we can just use the same terms basically as before. We can call them sinks. This is when the trajectories point in. Sinks are when the trajectories point in, and sources when the trajectories point out. We can call them specifically nodes if they are a sink or a source that is just a point. Sinks and sources. I'll just call sinks and sources. Nodes are sinks and sources, and then we can call them proper versus improper, just as before. Proper, so in other words, it's a star point, so straight in or out. So it makes a star point. Or improper, where they converge on a line, so that makes them look like this. And then we can also have saddle points. And the easiest way to see that is just to draw it. So let's say we have an eigenvector going that way, an eigenvector going that way, and then it goes in along one, out along the other. This corresponds, as you recall, to there being two real eigenvalues, one positive and one negative. And the negative one is the one that it comes in along, and the positive one is the one it goes out along. Anyway, so saddle points, centers. So these just make like circles or ellipses, not a spiral. And then spiral sinks. Where it's going, so these are going inward. And spiral sources. Alright, now what we specifically will also do is categorize these as being stable or unstable, and then also add in asymptotically stable. So stable. So what stable refers to basically is any kind of a sink or center. And an unstable critical point or an unstable equilibrium refers to a saddle point or a source. And then furthermore, and by sink and source, I'm including spiral or nodal, or spiral or otherwise. So we have stable and unstable points, and then there is asymptotically stable. which means basically stable but not a center. So in other words, just a straight up sink. Not a center. Sink or center, and by sink here we are including spiral sinks, so I should make a note of that. So I including spiral sinks. And here, this is including spiral sources. So right now we're just going to kind of eyeball systems and make our decisions based on the phase planes, but we'll have an actual rigorous way of determining what the nature of these critical points are going to be by using some eigenvalue stuff. But for now, we can look at direction fields and phase portraits to classify critical points. And the easiest way of doing this is by using an applet such as the Bluffton applet or a calculator. For example, using the applet at bluffton.edu or a calculator. Either way, your TI-89 style calculators can also do the direction fields. All right, so let's now actually take a look at the differential equation system that we were just finding the critical values of on that Bluffton website in order to classify these points. Okay, so in order to take a look at the system of differential equations in question, you just go with what is by now probably a well-trodden path of looking up slope field generators and just scrolling down till you get to the one from Bluffton University. What we are interested in here are systems, and so now let's say we want to put in the one that we were just talking about, which was 12x minus 3x squared minus xy. Put in the times on the xy. And then here, same thing, but 12y minus 3y squared minus x times y. Alright, and here specifically we are going to want to zoom this out a little bit because our critical points go out as far as positive and negative, go out as far as 4. They're all positives though, so I can just go -1 out to 5, and then -1 out to 5. Should be good. Alright, and then if you are in any doubt about what's going on around them, you can just put some, I should clear that. I should change my method from Euler, which is a little bit too coarse, to the Runge-Kutta method, for example, which makes a smoother picture. And we can see what's going on here, and we can put in a few a few of the spots here, and we can see that 3 appears to be a sink, and it looks to be an improper sink. Now the origin looks like a source, and in particular it appears to be a star point. So that will mean actually that it is that it, at least to the eye, appears to be a proper source. Let's see, 4, 0. That's over here. This one appears to be actually a. I should actually clear this up a little bit, and I should make my step size a little bit smaller, looks like, and maybe I should zoom out just a little bit more, give myself a little bit more room here. It's all an iterative process. You gotta figure out what's what by any means necessary. Change things if they need to be changed. Okay, so now I got a little bit more perspective on things. So now looking at this, what we see at the point for 0 is that it appears to be a saddle point, because you'll notice it's going in along this trajectory and it's going out along that trajectory. So again, we have what appears to be a star point here, since everything is coming out in basically a straight line, and then it starts to turn once it's out of there. We've got we got a sink up here that appears to be an improper sink. It really looks the part. And then over here at 0, 4, we appear to have again a saddle point, because we can see it going in towards the point from the vertical direction and then out from the point in the horizontal direction. So what we had was a star point at the origin, an improper sink at 3, 3, and then saddle points at 4, 0 and 0, 4. So now we can put all that information into a phase portrait to represent what is going on. So then we can tell for our example, which was again x prime equals 12x minus 3x squared minus xy, and y prime is equal to 12y minus 3y squared minus xy. We can tell visually that 0, 0 appears to be a proper nodal source. And then 3, 3 appears to be an improper nodal sink. And then 0, 4 and 4, 0, those both appear to be saddle points. And so putting all these pieces in there, we can actually draw some of the representative curves. So they'll be going out like this and like that. And then this one will be going out and then going into there. These ones are just going out. Here we have ones going that way, it seems. And then these ones, they go along there, but then they seem to go into that sink. So And then over here, what was the deal on those ones again? Let me take a quick look. So those ones were going out along the vertical, and here it would be going up like that, and in along the horizontal. So this would be a phase portrait. So it's going that way. So here I've just drawn by hand some of the representative curves that we would see. Okay. Now let's take a specific example. This is an example that actually the book covers in section 3.4, but I thought it was better to wait till now because we can actually see visually a little bit more that's going on here. So another example would be what is called free damped oscillation. So the setup here is that we've got a spring, we've got a mass attached to that spring. So here's the spring, and then a mass attached to the spring. This is a spring. Oops, spring. We've got a mass. And then what we've got is a representation of something which is sapping the force out of it, which is dampening the oscillation of the mass on the spring. And that's typically represented by what is called a dashpot visually, but practically speaking, what this really means is it's anything which is absorbing some of the force. So it's going to be, so it could be, for example, just friction. This is what's called a dashpot. But it's more general than the little muffler-looking shape that we've got here. It actually just represents in general some other force that is dampening the oscillations of this mass. So then we can put together several of the famous laws from the 17th century. We've got Newton's second law, most important law really in all of physics, which relates force, mass, and acceleration. So force equals mass times acceleration, which in this case would be mass times x double prime, where x is the position of the mass relative to the equilibrium of the spring. So every spring has a natural length that it wants to be, and if you were to squeeze it in or to stretch it out, it will bounce back and forth. Okay, now then we also have Hooke's law, which relates specifically to springs. And Hooke's law basically says that the force that a spring will exert on the mass, absent anything else, is going to be proportional, but negatively, to how far the mass has been stretched out from the rest spot of the spring, so the natural position of the spring. And then for the dashpot, the dashpot dampening force or friction we're going to assume that we are going to have a force that is going to be dampening the thing contrary to the direction that it is moving, so it is indeed absorbing it in a friction-y way, and it's going to have a constant c. And it's going to be proportional to the motion, so it's going to be like the kinetic friction is what's going on here. So putting these all together, what we'd have is mx double prime equals negative kx minus cx prime. Now, if we wanted to make this into a system, make a system where x will equal x and y will equal x prime, then the system we would be talking about would look like this. So x will equal x, y will equal x prime, and so x prime just equals x, as we've just said, but then m times x double prime is equal to negative kx minus cx prime. So this is going to be the same as m times y prime is equal to, and then over here what we've got is negative kx minus c times y. So then putting those together, we're going to have a y prime is equal to negative k over m x minus c over m y. So then the system will look like x prime, sorry, x prime equals y, x prime equals y, x prime equals y. Probably we're all slapping your foreheads for minutes on end there. Then y prime is equal to negative k over m times x minus c over m times y. So there's our system. And the behavior of it is going to depend on the relationship of the three parameters here of m, k, and c. But I want to make a quick note beforehand. So note, when we turn a second degree constant coefficient when we're taking a second degree constant coefficient ordinary differential equation into a system, the characteristic equation used to solve the original ODE, so that's the so it's going to be the quadratic equation in R, will be equivalent to the characteristic equation used to find the eigenvalues. So when we do the business of finding the R in order to get the solutions to the second order differential equation, that equation, the characteristic equation there, it's not a coincidence that it is called the same thing as what we do to find the lambda. So based on this, we can actually figure out what the eigenvalues will be from any of the original versions of the equations. So thus, we can find the eigenvalues of this system by looking at the mx double prime equals negative kx minus cx prime version of things, which will then be mx double prime and then plus cx prime plus kx equals 0. But then this is the same as the second derivative of x times m plus the first derivative of x times c plus just k applied to x. And that means m r squared plus c r plus k equals 0. So just changing it from the differential operator. And then that means that r is going to equal, according to the quadratic formula, in this case, negative c plus minus. And then here we're going to have c squared minus 4 times m times k, all divided by 2m. And what that means is that the lambda here will be determined by this. So going back to the system, what we have was x prime equals y, y prime equals negative k over m x minus c over m. The eigenvalues will be lambda equals negative c plus minus square root c squared minus 4mk. And actually, before we note, sorry, this should be times y right here. And before we go any further, we should note that the critical point here is going to be at the origin. So 0, 0. And then we've got the eigenvalues here. So this is just purely linear here. Over 2m. And so the nature of the critical point will depend on the discriminant. Sometimes delta is used for the discriminant. c squared minus 4mk. So if the discriminant is positive, there will be two real and in fact negative eigenvalues, which will mean a nodal sink. Going to be improper. If, on the other hand, lambda equals 0, it's going to be 1 repeated negative eigenvalue. And we'll let the, and from the picture we'll see that this one is going to be proper. And then finally, if lambda is less than 0, we're going to get 2 complex eigenvalues, and here with negative real parts. Which leads to the conclusion that we're going to have a spiral sink. Now let's actually look at examples of this, and we're going to consult the Bluffton on this matter. But first, let's do some of the math to begin with. So first off, so case 1. So this is delta greater than 0, and this is what's called an overdamped system. So then what we will get is, so this is the spiral. So this is the improper nodal case. What this is going to then look like is via Bluffton, an example like there. So first we'll write the numbers, and then we'll look at it on Bluffton. So for overdamped, we could say m equals 1. We could say k equals 5, and here c equals 6. So then the lambda will be -6 plus minus, and here you can see why we know they're going to be negative from the way this all shakes out. Here we have c squared is 36 minus 4ac divided by 2m. -6 plus minus, that's going to be 16, so square root of that's going to be 4 divided by 2. So on the plus side, that's going to be -2 over 2 is going to be -1. And on the minus side, that's going to be -10 over 2, so it's going to be -5. And so the x prime equals y, and the y prime equals -k over m, so -5x minus 6y. So this is going to give us via Bluffton the following. Alright, so I have now taken the liberty of bringing up Bluffton, putting in this equation, or the system of equations with these parameters, and now let's just see what it looks like. So you got here, the improper nodal sink, and it's got that kind of swirly variety. It looks almost like a spiral, but it's not a spiral because you can see that everything is actually just coming in along that one line, and that one line represents the eigenvector, the one real eigenvector that there was, or sorry, it represents the eigenvector that we had for the negative value of t. Or sorry, this is so as t gets bigger, so this is going to be the less negative of them. So anyway, it doesn't matter. So here what we have is some of the trajectories, and then we can also actually look at the time plot. Now remember, it's actually only the x that is really relevant here. The y was more or less an invented situation, but look at what happened with the x. So with the x value, it was so it's the red one. So it was distended, and it just immediately flipped back into the equilibrium because it was so damped that it didn't have time to do any oscillating whatsoever. From Bluffton, we got the phase portrait. It was going in like that, and it was doing one of those things where it was going. Anyway, so it's going like that. So it's got the actually, what am I doing? So it's going in towards the origin. That last one. So it's a nodal sink, and it's improper. So it's an improper node, and then the time plot. And here we're only interested in the x. So this is for a specific initial condition. The time plot there was just basically going like this. So no oscillation. So it's too much. Too much dampening. Alright. Now, let's take as a second case we'll take the case where we end up with the delta exactly equaling 0. So case 2. So this is the discriminant equals 0. And this is an example of what's called a critically damped system. So it's critically damped. And we can take here as an example m equals 1. We can take k equals so k equals 9 and c equals 6. So then what that means is that lambda would be equal to, and it would be negative c, so negative 6, plus minus the square root of 36 minus 4 times a times c, so 4 times k times m, so that's going to be 36, all divided by 2a, so that's going to be just equal to negative 3 with multiplicity 2. So we know that this is a repeated eigenvalue, which actually doesn't directly tell us whether we are going to be expecting, or what exactly we're going to be expecting to see here. But that's why we again just go to Bluffton to find out. So we would have to crunch the numbers, find the eigenvector if we wanted to analyze this. But for now, let's just let the computer do the hard work for us. So back to Bluffton. Okay, here I have once again taken the liberty of putting in the system as we made it, and now if we look at the appearance, it doesn't look very different. It looks pretty similar, but it's right on the threshold of the dampening. And now if we look at the time plot, you can see on the x, it's got just the tiniest amount of wiggle back and forth, very, very mild amount, but it almost immediately is all dampened down. So then from the Bluffton, we again had a very similar looking expression, or direction field. However, the difference, so this one, however, is right on the boundary of this sort of behavior. So technically here, what we saw was it coming in like so. And now it's a little bit more swoop to it. And the most important difference here is wait, what am I doing? Shit, that's not quite right. There it goes. Okay, anyway, so it's doing something like that, and then for the time plot here, we had a slightly different behavior in that it wiggled ever so slightly. So let me see here. So it went. So it almost oscillates. Okay, so this one almost oscillates. And then the last case here is case 3, which is going to be what is called underdamped. So this is if the discriminant is less than 0. This is underdamped. And we can have a case of m equals 1, k equals 5, and c equals 2 for something like this. And then what that's going to give us is the lambda is going to equal -2 plus minus the square root of. And here we're going to have 4 minus 4ac, so minus 20 divided by 2a. So it's going to be -2 plus minus. It's going to be -16, so it's going to be 4i all divided by 2. It's going to be the -1 and plus minus 2i. And so it's going to be a spiral with negative real parts, so it's going to be a spiral sink. And now let's have a look at what that looks like on Bluffton. Alright, once again, here we are, and here's the direction field, and let's follow a few solution curves. So we got one going that way, one going this way. And you'll see that you can see them spiraling their way all in. And then as far as what that actually means for the spring, for the mass on the spring, is that it will actually then undergo some oscillations. So in fact, you can see here it continues actually to oscillate, and technically it would continue to do that forever. That's what makes this an underdamped system. However, practically speaking, at some point it would eventually stop. All right, and then Bluffton gave us spiraling inward, lots of solutions like that, and then the way the time plot looked. Then the way the time plot looked here, we have x and we have t, and it was doing some oscillations of ever lower amplitude, but they continued on forever. So the x1 was going like this, and then it went up, and then it went back down, and then it went back up, and it's a little bit exaggerated, but essentially it continues oscillating but with lower and lower amplitude. And actually, at this point right now, if you would dig up the notes a few pages back, right here, this was a typo. It should be improper on the discriminant equaling 0 case. So this is improper. And that's a thing that it would have required us finding the eigenvectors and such if we wanted to do it analytically, but in fact we were able to see it just visually in this case on the Bluffton. So it's an improper nodal sink. So that edit, go back on this little if delta this, if delta that, make sure you fix that to improper. Okay, and that will do it for this. Join me next time for the next episode of Math 256. Until then, bye.